Next in this video, we will consider cross-validation, which is a resampling technique. One of the resampling methods. It has many purposes of usage, but in the context of system identification, we explain the cross-validation as a way to pick a model or in the model selection process. So as we see before, when you consider the model, we have the term training error rate, which is the error you evaluate the trained model on the training data set. The test error rate, on the other hand, is the average error that you want to conclude that is a generalization, is a generalized error you evaluate on the new observation on the unseen data set. All right. So these two guys can be different, all right? Sometimes you see that the training error rate is small, but the test error is high, all right? Cross-validation is a way, what we're about to explain. Cross-validation is a way to estimate the test error rate using the available data. Now we're going to use the available data and split it into the training and the validation sets. And the way we can split these two guys can be done by the following three approaches. Okay. So this is how you split data. From this figure, the blue one, the blue tones, we're going to refer it to the training data set. This is the portion of data you use to estimate the model to fit. And the beige color is going to be the validation data set. This is to predict the response using the estimated model, and we're going to evaluate the error on this portion on the validation set. All right, now let's see how we split the data using three approaches. The first one is called validation set approach or holdout. This is a term they use in machine learning. This is the left part. This is what we do. Suppose you have, sorry, we use small n here. It's supposed to be big N. Suppose you have big N samples, all right? And then the way you do is you shuffle the data in the randomized way. Suppose I shuffle it like the label of, this is not a label, like, you know, the index of the samples, all right? 7, 22, 13, all the way down to 91. Once I shuffle it, I cut it, I split it into two separate sets with the ratio that with an appropriate ratio, for example, 70, 30. This ratio is just a rule of thumb, but you always select the estimation data set to be a bigger portion than the validation, because you know that the number of samples in the training data set affects the quality of model parameters. Okay, this is the first one. So the holdout approach, all right, the way you obtain the validation in the blue one is also random, because it depends on like the instance of randomization in one run, which means if Popok split the data, Popok will get this estimation. It would be different from another run. For example, if Ping perform this again, Ping will shuffle the data and you will get the different portions, right? So which means splitting in this way in holdout approach, for many runs, you will have different sets of training and validation. Okay. The second one is called leave one out. All right, leave one out cross validation, the one in the middle. The way you do it is the following. You just leave one out, leave one sample out for validation. And the blue one, of course, the blue one contains, how many sample contains in the training data set in this case? Total?
100 sample.
What do you mean 100? The total number of data points are n, big N, all right? So in leave one out, you leave one sample out.
Yeah, so the training data has n minus 1.
Has n minus 1, all right? Again, you use the blue portion to estimate theta hat, all right? And you will use this model theta hat to compute MSE as a way. This is can be any index that represents the model error, all right? Let's say I use MSE. I label it as MSE1 because I evaluate MSE1 on the first sample, the one that you left out. Okay, now not finished yet. I'm gonna do the loop. I'm gonna take the second sample out, all right? And I do the same. I combine the blue portion, I compute theta hat, and I use that theta hat to compute MST2. Okay. Ping theta hat 1 and theta hat 2, are they the same?
No, Ajahn.
Why they are not the same?
Because we choose the different sample of data.
Okay.
So it's a bit different.
All right. You continue doing this until what? Until all the samples are left out as validation. All right. So when you perform this, you can see that, oh, this is gonna require a loop. All right. So this is the loop that run from k equals n to total. How many times do we have to perform this?
N times.
N times, right? And big N, let me just use it to big N. All right, so you will obtain MSEN, like you have N values of MSE. In this way, the cross-validation error from this splitting approach is given by the summation of, the average, basically, the average of MSE that you obtain from each validation samples. All right. Now the last one, the last technique is called K4 cross validation. In this splitting technique, first you shuffle the data. You randomize the index. All right. You randomize it. Now let's say when you randomize it, the first one start by index 11, 76, and so on. Now you pick the number of k, and the the typical choice like 10 to 5 to 10. All right. So you're gonna chop it into five folds. For example, k is 5. All right. And then you leave one fold out for validation. So you're gonna combine how many folds in the blue one, how many folds you have in the training process total?
4 folds.
4 folds, or k minus 1 folds for training. Again, you compute theta hat and you use that theta hat to evaluate MSE1, which refer to the MSE evaluate on one fold you left for validation. And now you continue. You move to another fold. You move to the second fold that is left out for validation. So you perform this until all the folds have used for validation. How many times do we run here, Ping?
5 times, Ajahn.
Which is five times. K times, right? If you pick k folds. Okay. In this case, we see that the cross-validation error obtained by k-fold is actually the average of MSEK. K run from 1 to k, the number of folds, divided by k. So the average over k folds. For leave one out is the average over n samples. Okay. All right. Now let's examine this a little bit more. In terms of computation, okay, which one between leave one out and K4, which one require more computation efforts total?
Leave one out.
Leave one out, right? Because think about you have like 1,000 samples you have to run for 1,000 times. You have to estimate the model for 1,000 times, right? Now let's take a look at the behavior of theta hat. All right, we see that in both cases, in both leave one out and k-fold, when you estimate theta hat, those theta hat from different training sets, they are not the same. They are not exactly the same. But let's focus on the leave one out. All right. When we take a look at the portion of data, now I'm going to remove everything. Like, okay, now we're going to consider the first one and the second one. Think about the blue area. The blue area are the portion for estimation, right, data. Are they very highly overlapped or they are completely different, these two data sets, these two training data? Ping.
I don't understand your question. What different?
See the blue area in these two cases. These blue areas are the portion of estimation data. All right. So I'm asking how these two blue regions are overlapped.
Overlap.
How many terms, how many samples are overlapped between these two regions?
Oh, n minus 2.
N minus 2, right?
Yes.
Remember the portion of training set is N minus 1, but there are N minus 2 that are overlapped, right? When they are highly overlapped, of course, when we say that, oh, theta 1 hat and theta 2 hat, they're not exactly the same, but do you think they are very correlated? They use almost the same, right? Almost the same data set for estimation. Of course, these two guys will be highly correlated. Okay, in that sense. So this is a property. Now let's take a look at the results. What we're going to do is, so the cross-validation process can be used in model selection, can be used in tuning some parameter of the models, can be used in comparison, in comparing two model type as well. Can be used for many purposes. Now let's take a look in the model selection point of view. All right. Okay. Oh, this is the problem of choosing the polynomial model, polynomial order. So we run the k-folds, 5 folds. We run the holdout for 7 times. All right. Now let's take a look at the. So for the holdout, as I said, for one run, you randomize, you shuffle the data, and you split it into 2 sets. This is one run. For the second run, I randomize, I shuffle the data in another way, in another random way. So of course, validation and test that I split in the second run would be different from the first one. Okay, here I plot the model order that represent the model complexity, and I plot the MSE. That is the MSE on validation sets. From 7 run, you will see that these MSE curves that is supposed to be, right, the MSE that we obtain, the cross-validation MSE, is used as a way to approximate the test error. The true test error rate is often unknown unless you know the true description of the model, which is apparently not the realistic assumption. All right. Okay, you see that all the MSE graphs here, they are all different. They are highly fluctuated. Not highly, I would just say, I probably just say that they are fluctuated. They are vary, right? By different runs. but they seem to have a common ground on the significant gap when the model order that reduce the MSE significantly is about a model of order 4. Okay. Now the 5-fold CV, what do you see? Of course, for the 5-fold CV, for one run, when you perform cross-validation one time, you get 5 folds, you run estimation for 5 times, right? That's one run. And that one run is one graph. Again, if I perform 5-fold cross-validation again in another run, those 5 folds that you split would be different from the first one. Let me recall this again, right? Because this is one run that contains five times of computing. Like, because in a single run you shuffle the data, so the index that you obtain in each fold would be obtained in a random way. So in the 5-fold cross-validation, what's the main significance? 7 runs here in the cross K4 and the 7 runs in the holdout. You see that cross-validation error estimated by 5 folds has less variation than the holdout approach. It's less variation because the MSE that you obtain from cross-validation is already an average version. All right, it's already an average version. For leave-one out, of course, you perform leave-one out just once. You already use all the samples for accounting for computing the MSE. All right, so you run. I mean, of course, it has only a single graph, because if you run the leave-one out again, you get the same result. All right. So all the 3 approach seems to agree that the model order picked by the cross-validation approach seem to pick model order 4. But the cross-validation error obtained from each one is different. If you're going to use MSE as a way, if you're going to use a cross-validation error as a way to estimate the test MSE, these 3 approaches are different. These 2 guys, the value might be similar, but it's different. They are different by the computational effort. All right, this one is more computationally demanding. Now let's take a look. Continuing from the previous slide, that's a cross-validation is a way to estimate the true test error. This slide just show that we run simulation on the toy example. It's a toy example that you assume the true density, the true model, which means that you can compute the true test MSE from this example. Like you're the one who define the true relationship as a mathematical expression. So the true test MSE is represented by the blue graph. Okay, and we have the orange and the black graphs as cross-validation error obtained from 2 approaches. All right, and we see how the cross-validation error can estimate the true test error. From the first one, you see that the cross-validation seems to underestimate the cost, because the graph is underestimate the true test error, which is not desirable. All right, because you think that, oh, the error is this low, but the actual error is higher. Okay, in the second case, all right, when in the true test error, when the model F, the true model F is close to linear, this is where we observe that the cross-validation, the error you estimate in the in this zone when the model is complex, the cross-validation's error seems to overestimate the true test error. When f is far from linear, when the true model is actually complex, right? In this case, you see that the cross-validation error seems to approximate the true test error very well. Okay, so as a role of cross-validation error for approximating the true test error, sometimes you overestimate it, sometimes you underestimate it, but the model complexity selected by cross-validation approach, the true one, the approximate one, true one, approximate one, seems to be acceptable, which means that the model that you pick somehow close enough to the true complexity. All right. We also mentioned that the cross-validation approach can be used in other purposes as well. So I would like to go back to the lasso problem. Recall that the lasso problem, this is optimization problem where you wanna find sparse x, right? Sparse x represent, let me use beta, so that it agree with our notation here. You minimize y minus x beta square plus gamma norm of beta 1. You prefer a beta to be sparse, which means a lot of coefficients go to 0, which means you use less number of features by using the L1 norm. In the lasso problem, of course, gamma represents the control, right? Gamma is big, your model is simple, right? Because it has lower number of coefficients. If gamma is small, your model is complex, which means gamma is a parameter that refer to model complexity. So what is the appropriate choice of penalty in the lasso? So choosing gamma can be done in many ways. Model selection score is one of them, but now I'm explaining how you can use cross-validation. So which means for one particular value of gamma, you perform the cross-validation. So let's say you perform K4, you have to run K times and you get cross-validation 1. Again, vary gamma 2, another values of gamma 2, you get CV2, CV, and so on. All right. So suppose M value, you get CVM. And then you can plot this graph, and that's the graph that's the first graph on the left-hand side. All right. And of course, you pick gamma that obtain the minimum cross-validation error. Okay. Now in the second graph, I'm not going to the detail, but it's basically meant that for each gamma, you can use the model selection score. Okay. And again, you select gamma that obtain the minimum AAC or the minimum BIC. From these two graphs, can you see total K4, AIC, and BIC? Which score select the highest penalty gamma?
AIC.
BIC, right? So highest value of gamma means sparse model or dense model?
Sparse model, simpler
Sparse
model.
model, right? So it all agree with the property of this score we learned before. BIC typically prefer a simpler model. That's why BIC often pick large values of gamma, which is a penalty in the lasso term. All right. Okay, that's about it. We run out of time, but I would like to continue the lecture. Toto, if you need to go to the other lecture, it's fine, but just a few slides left. I would like to complete it. So we have done with the model selection approach. One approach is model selection score. The other approach is to use the cross-validation. Now we're talking about the final steps of system identification process. Once you pick the model, right, you have candidates, and now you pick the one that is best in some sense, is best in the sense of BIC, for example, is best in the sense of cross-validation. Now we're going to validate if this model is good enough for your purpose. And the purpose of you estimate the model in the first place is different from one application to another application. Someone use it for controller design, someone use it for model inference, right? And other things. So in this step, model validation, it has many aspects, all right? If you use model for controller design, the physical parameter has some meaning, or it has to be, you know, lie in some interval. For example, we see before, when you estimate a dynamical model, you want the model to be stable, all right? And that implicitly require the feasibility of physical parameters. You probably want to take a look at the model order. Sometimes you prefer simple model, but I mean, it all depends on the selected model in the selection process. All right. If the selected model is still complex for you, now you have to kind of tune in this final process. If this selected model also require a further model selection, model orders reduction. Okay. You may also take a look at the statistical point of view, where once I obtain theta hat, which is a point estimate, remember all the estimators are random. The model parameters that you estimated is also a random value. We call it point estimate. How are we confident that these values should be used, all right, for new data set? You can take a look at this as like one way to use as more information is confidence level, which means you provide upper bound and lower bound, all right, and see like the possibility that the true parameter lies in this interval, all right. Okay. We're going to provide 3 basic tests in order to validate the models. All right. Here we rely on the DGP that your Y is a function of input and it has some noise perturbed. Your model, all right, G and H is a true description. But in your model, probably you assume G tilde and H tilde. And of course, your G tilde might not be the same as G. Your H tilde might not be the same as H, because the DGP is always unknown. All right. Use epsilon for prediction error. Now let's go through these 3 tests one by one. Okay. If I subtract YT, Y hat T from YT to compute the residual error, then I get this equation. You will see that the prediction, the residual error, is actually results from the discrepancy in the assumed model from the 2 model. Okay. This is G minus G hat and S minus H hat. Okay. Now we can use the cross correlation. This is cross correlation of covariance error. It is also a function of time. All right. Now let's take a look closely to this green term. This green term, if, of course, if your H hat is not equal to H, like your assumed model, especially on the part of the noise dynamic, if you have a very wrong approximate of H hat, it means that this guy is non-zero. This transfer function is non-zero. So you can take a look at this term as a filter version of the noise, because it's the noise that passed through this transfer function, non-zero transfer function. So E is the corrupted noise in the true model. This E, remember that we typically assume E to be what? We typically often assume E to be white noise, which means the covariance of the autocovariance of noise at different time is a delta function. The noise at time t doesn't have any correlation at time s. This is the property of white noise. Again, if I draw autocorrelation of white noise, if something white noise, it has this delta function of the autocorrelation. But then when the white noise pass through some transfer function that is non-zero, the result is called color noise. When you have color noise, the autocorrelation is no longer white, which means, the autocorrelation is no longer a delta function. Okay, so at tau lag 1 or 2, it might have some non-zero autocorrelation. So we can use this fact as a way to perform a statistical test if the residual error, all right, resembles a white noise. If the prediction error is close to white noise, it means these test statistic, which is basically the sum of autocorrelation of residual error, these guys should be small. Because it's a sum of like many time lags. And it can be proved that this test statistic has a asymptotically chi-square distribution. So if this test statistic is significantly bigger than the critical value, so we're gonna reject the null hypothesis which is the null hypothesis is the model that you assume is the model. Okay. So when we reject it, which means that the part where you assume h hat is not good enough, right? Because it results in non-white residual error. So you need to improve this part of the transfer function. You need to improve this guy. All right. For example, if you are I use different notation. So if you assume that h hat is I, all right, and the test suggests that your residual error is not white, maybe you need to assume some transfer function in h hat, not just a constant. Okay. This is called the white test of the residuals. The next test is a cross-correlation test. The cross-correlation test says that, now let me go back to this equation, is G minus G hat U plus H and S hat E, all right? Now we take a look at this portion. The residual error also results from the discrepancy in the G term. It's a transfer function from U, deterministic input, control input to your signal. Okay. So if G hat match G perfectly, all right? If G hat equal to G, this term goes away, right? This term go to 0, which means dynamics in the input will no longer be present in the residual error. Which means if that's the case, the cross correlation between the residual error and the input U should be 0, because your residual error doesn't contain information about U at all, right? On the other hand, of course, if G minus G hat is non-zero, we can say that you're gonna have some which means you're gonna have some dynamics. Residual error still contains some dynamic in U. Residual error still is a function of U, And when you compute the cross correlation between residual error and U, it's still a non-zero cross correlation. Of course, we can use this idea to perform a hypothesis test. The hypothesis test with the null hypothesis as cross correlation is 0, which basically means G hat is good enough, all right? G hat, match the true transfer function. And then we compute the test statistic that based on, there's more detail in my textbook and Lung textbook as well. It used the it used R as a sample cross correlation of this guy. All right, this is quadratic in R. And normalized by autocorrelation of residual error, autocorrelation of the input. There's a more detail in computing this test statistic, but basically it means that this W is a normalized version of the sample, normalized version of quadratic function of the sample cross correlation. So the bigger the test statistic means it gives a sense that the bigger value in the cross correlation. So in the test, if the test statistic is bigger, statistically significant, means it means that we reject the null hypothesis, which also further means that you must correct your G hat part. You have to improve it, which means you need to improve the complexity. For example, it might be possible that your G, for example, your G is fourth order. For example, fourth order transfer function, but now in your model, your G hat is only first order, right? And then you perform the cross correlation test, it fails, right? You reject the null hypothesis. So you come back here and what? And probably you can increase the model complexity, all right, and do again. So here's some results. So all the two tests are called residual tests because it uses residual error, prediction error to perform cross correlation and autocorrelation. All right. Now we see the true system is Rmax 223. All right. This is the order of autoregressive, moving average, and oh, sorry. I think 2 is autoregressive, right? 2 here is exogenous term, 3 here is a moving average term. Oh, the other way around, sorry. So 2 here is AR term, 2 here is MA term, 3 here is exogenous term, all right? So, and our model has two choices, ARX and Rmax. ARX is obtained by the orange curve. The Rmax is obtained by the blue curve. All right. So in this graph, these blue and pink area, these are the acceptance region from the test. All right. Which means if the correlation function values lies in this region, all right, then we the model is acceptable. Okay. So which means we accept the null hypothesis of this cross correlation is 0. Okay. Now let's see. In the first case, this is this is autocorrelation or the white test in the worst. What do we see? We see of course, at lag 0, the correlation must be non-zero, must be at maximum. You see that the model ARX has some lag, right? Exceed the acceptance region, which means the ARX model, all right, need to improve on the edge part, the transfer function from the noise to output. And that makes sense because your true model contains the moving average part, but in your model, you use ARX that contain no moving average term, right? In ARX, it can be seen that your H hat is only I. Okay, so so here ARX doesn't pass the white test. Now let's take a look at the cross correlation. This is to test whether the G part, the transfer function from input to output, is appropriate, is acceptable. So you see roughly, even though the orange one, the ARX one, kind of, has one lag exceed the acceptance region, but we can see overall that both models seem to pass the test cross correlation test, which means the G hat part from these two models are are appropriate enough or are complex enough in order to explain G, right? Because, and as you can see here, because the X term, exogenous term, is they are from third order. Another point of view, all right, this is another point of view is about the model order. When the model is over parameterized, which is the model is too complex, sometimes you can see a chance of zero pole cancellation. So here's the same example, but oh no, not the same example, sorry. We have Rmax models of two complexity degrees. Okay, and the sixth order is given by the orange marks. You see that when you pick higher order model, you plot zero pole on the plane. Pole, the cross sign is pole. The circle are the zeros. So you see that there are many pairs, right? There are many pairs that are that seem to be cancelled, which means if you have this plot, and this kind of indicates that the model is too complex. The higher order is probably can be reduced. Okay. So all of these in this test can be obtained from the MATLAB command, the residual analysis, resid. You can compare between these two models, get the Songsiri plot, and compute the fit percent using the compare command. From these zero pole plot is given by IOP Z plot. All right. And so I would like to conclude this chapter that is about the model selection, the model validation as the two final states of performing system identification. And these are all the reference.